So it gives me pleasure to announce Team 254. Did I get that right?
Yep. Yes.
Good, okay. And they're going to talk about the first robot competition. Thank you very much. Okay.
Hi, everybody. My name is Andrew Torrance. I am the team president for a high school first robotics competition team. And my friend here, this is Ryan Johnson. He is our director of programming and controls. And so he will, later on in the presentation, be talking about a new control system that our robots are using this year. But before we get to that, we're going to talk a little bit about robotics in general. But first, I got a cool thing to show you guys.
Oh, sound turned up. You're gonna have to hold this up.
We're going to talk more about that robot a little bit later, but it's pretty cool, I'll just put it that way. So I mentioned that we are a FIRST robotics team. FIRST is an acronym for an organization. It stands for Inspiration and Recognition of Science and Technology. And FIRST itself is actually an organization that's been around for a long time. It was founded all the way back in 1992 by inventor Dean Kamen. Little quiz. Anyone know what else Dean Kamen is for? Just shout it out. Segway. Yes, Dean Kamen, the inventor of the Segway, is also the founder of FIRST. The big thing about FIRST is that the students work with industry professional mentors. So compared to other robotics programs that students can participate in, FIRST, and particularly FRC, the highest level competition, is one where you're working with mentors. We have some of our mentors back there. If you guys want to meet them, they're pretty cool guys. So just the whole point of the program is that you're being inspired to pursue science, technology, engineering, and math in either a college major or a career later on. And you're also learning the engineering process in both technical and non-technical skills, such as how to give a presentation. So FRC, the first robotics competition I mentioned, is the highest level competition out of the 4 that FIRST runs. FRC is often called the sport for the mind because it's really the highest level varsity robotics competition that you could do in high school. They always use this phrase, it's the hardest fun you'll ever have, and I can definitely confirm that. It's very difficult to pull off what we do in FRC, but it's definitely worth it. It's tons of fun. There are now over 3,000 teams from around the world. That includes countries such as Brazil and Israel and tons of teams in Canada. So when we go to the World Championships, we get to meet tons of different people. Now FRC has a very interesting timeline. If you start looking at some of these dates, you'll see that there's a kickoff that happens right at the beginning of the year, right as we get back for the second semester of school. And then we only have 6 weeks to build a robot. So that kickoff, they tell us a game challenge, and we have to play that game, and that game challenge changes every single year. So you have a new robot with new strategies each year. You only have 6 weeks to build your robot. So, you know, when you talk about all the different things that you have to do to build a robot, you have to brainstorm how are you going to score the points. Then you got to, you know, prototype different mechanisms that can do that. You have to machine the parts, assemble the parts, weld the parts, powder coat, anodize. It goes on and on and on. So 6 weeks is definitely brutal, but it also makes you learn a lot. Then you have a bag and tag day or stop build day. That happens in February. Then you go to the fun part. You have 6 weeks of regionals. Not every team does all 6 regionals. Most of the time teams go to only 1 or 2. But at these regionals, there's more than 30 teams, and you're all competing in short 2-minute matches to try to see who will score the most points and end up winning in the end. And as I mentioned, there's a world championship with all of the teams from around the country. That happens in April. That's definitely the highlight of any student's year that participates in it. So just a little bit more about us. We're Team 254. We're from Bellevue College Prep in San Jose. And our little nickname there is the Cheesy Poofs.
Cheesy Poofs.
If you're really interested, I would love to tell you the story behind how we got that name, but maybe you can guess. A little bit about our team history. We're a pretty old team. If you see other FRC teams, you can kind of get an estimate of how old they are based on the number of their team. So we're 254, pretty low number relative to about 3,000, 4,000 that the teams are getting to now. So we were founded back in 1999. And actually in 2004, we won the Chairman's Award, which is like the award for the most overall excellence in both technical and non-technical fields. When it comes to technical, as far as winning tournaments, our team has been pretty successful. We have 37 blue banners. Wow. It's just like a trophy, but it's a very large blue banner, and it's really fun because you can wear it like a cape. Trust me, I've done it. And then comes the coolest part. We have won the World Championships twice, once in 2011 and then again last spring. And so that robot there on the right, that is our World Championship winning robot from 2014. And at the end of the presentation, we'll be doing a little bit of a demo with it to show you. It's pretty cool. So I want to show a quick match. This is the final match of the World Championships. We had to play against 100 other teams in our division. And then we had to go to the interdivision finals, called Einstein is the last field. And there you're competing against the champions of the other 3 divisions. So there's 400 total teams. We're in like the top 12 at this point. And we're with 2 other robots on our side. And our robot, if you haven't spotted it already, is about middle of the field on the left side. It has 3 large yoga balls. And you're going to see it autonomously score those 3 yoga balls into a goal in the bottom left corner.
What was this game called?
This game is called Aerial Assist.
Wow.
And you scored over defense.
We were scoring over a low goal and another robot that was trying to block us. So that was all autonomous. We only had 10 seconds to do that. That scored us 65 points by ourselves.
Wow.
Now we're in a teleoperated mode where a student is using a driver control joystick, kind of like playing a video game, to drive around the robot. It's definitely more stressful than playing any video game. One of the features our robot can do is we try to pick up that yoga ball. You can see us when I'm trying to chase it across the field and accidentally bounce out of our robot. Once we get it in our possession, our robot is unique compared to others because it actually fully encompasses the ball, giving us really good hold. The ball can't get knocked out of us. We get in front of that low goal in the corner, and then we can shoot up into the high goal. Shooting higher scores you more points than if you just try to put it in the low goal. So we always try to shoot higher up. The big point about this game, without explaining too many of the rules and logistics, is that you want to inbound the ball from the end of the field, and then you want to pass it from robot to robot down to the left end of the field and shoot it up into those goals. Basically like playing basketball, where you inbound at the end of the court and you pass, shoot. So you're going to see in the top right corner, we're going to inbound a ball into one of our partner robots. This robot was not built by us. That team's actually from Texas. We pass it to another one of our partner robot. That team's from Michigan, 469. They truss the ball over that large metal structure. That gives you extra points. You throw it back into our robot, and our robot receives it. We drive over it into the corner despite having a defense on us, and we get it back up to the logo.
Put it in.
Say again?
A person caught it and put it in.
Yes. We actually have humans that interact with the robot. So it's a human that loads the ball into the robot initially, and then the robots have to be the ones that actually move the ball down the field. But you can do something to help your alliance, which is by after you trust that ball, you can actually catch it. So you'll see that in just a second. 469. We're in the final seconds of the match now. 469 trusses it to us. Our human player loads it into a robot. There's 12 seconds left. We're down 15 points. This is the final match. We end up scoring it in like a last second shot. There's like 5 seconds left. And we're going to try and go for one last trust shot. Buzzer beater. There we go.
Nice.
could hear the crowd's reaction in the background, that's probably the most exciting part about FRC, is that you're in a huge stadium and you have like thousands of people cheering at your robot or cheering against a robot. I would say about half were against us. So these are some of our recent robots. You see, we try to follow a similar design aesthetic. They're all blue because our school color's blue. And this one on the left is, one is Slipstream. It was from 2011. And that robot was able to pick up inner tubes, and that robot also became a world championship winner robot. This one on the top right, this is Overkill. It's called Overkill because what it was able to do was actually pull itself up a series of Jungle Gym style rungs and get all the way to the top of this pyramid in like only 7 seconds. And so we had to put some crazy amounts of motor and torque on that thing to lift that 120-pound robot that fast in the air. So that robot was pretty overkill. And then in the bottom right here we have Skyfire. That robot actually picked up small foam basketballs and shot them into a hoop. That robot was pretty cool too. That was my freshman year. So I mentioned that FRC gives you a new game every year, and because January 3rd has already passed, there's a new game for 2015. This year's game is called Recycle Rush. Has a cool little recycle logo there. I should give you the hint. This whole game is themed around recycling. So this slide is a little bit hard to read, but in the center of the field, you can see there's this divider which separates a blue side from a red side. One of the most unique things about this year's game compared to any other FRC game that you may have seen or heard of or whatever, the one I just showed you, is that that step there prevents the blue alliance from actually ever touching the red alliance, which means that this game is not about playing defense or blocking or going around your opponents, but rather about building an extremely efficient robot. Now, what do I mean when I say efficient? I mean efficient at getting points. And how do you get points? That is the fun part. There's like 1,000 ways to score points in this game, and we actually had to make a periodic table to keep track of it all. So on the bottom row, you can see the number of points you score for all these different permutations of things that you can do with the various game elements. The gray rectangles represent a plastic tote, which is only about 2.5 feet by 1.5 feet in size and about 1 foot tall. So it's a pretty large object relative to the size of the robot, and it's also very thick plastic, so it weighs quite a bit. And the goal of the game is to try to stack up these totes, as many as you can, and the higher you go, the more the green recycling can is actually worth. So you can see that when you get up all the way to these stacks of 6, the max you can go, your recycling can is actually worth ridiculous amounts of points. So one of the big strategies in this year's game is trying to build these really tall stacks of really heavy totes that are super wobbly, and it's almost a nightmare, but we're managing, kind of, sort of. It's okay.
You say totes, is that like a bag or something?
Not like a tote bag. It's basically a large plastic box. Storage container, pretty much, yeah. So it has like a lid, but the lid stays closed during the game. They zip tie the lid shut. So it's just a large rectangular prism, essentially. But it has slightly trapezoidal sides, so you can't pick it up with a scoop. And this year's game is definitely one of the hardest games they've ever given us. So in the end, we don't have a robot to show you yet because we're still building it. But we do have a drive base here. So at the end of the presentation, we're going to want like the video on this after we've talked about the control system, because this drive base actually is wired up, or 2/3 wired up, with the new control system that looks super cool and is super awesome. So speaking of a new control system, I'm going to pass it over to Ryan, our programming and controls director, and he's going to talk about that.
What grade are you guys in?
I'm a senior.
I'm a sophomore.
Okay.
All right. So I'm going to talk about the control system for this year, which is different than previous years. So first we have an overview. I know this looks a little intimidating, but the major components we're going to talk about is the PDP here, power distribution panel, the pneumatics control module, the voltage regulator module, and then of course the RoboRIO, which is the brain of the robot. So first we're going to talk about the RoboRIO. So the RoboRIO has a bunch of these specs you can see here. not impressive compared to a laptop, but over previous years, it's a huge increase in power, doubling its memory, both non-volatile and volatile. Also, it's combined 2 units into one, where we used to have a digital sidecar and the RoboRIO, which is actually on the old robot over there. It combined them both into one now, so you have less space taken up on your drive base for control system elements.
Is that controller commercially available, and how much does it cost?
How much it costs?
I think it's like $435.
Yeah, it comes in the kit of parts though for FRC teams. National Instruments makes it, and so because it's combined, it has less ports than it did previously. So what they've done is they've added this expansion port, which I'll talk about a little bit later, but allows us to have more ports than what it has just on it. So here are some sensors and motors that you plug into the RoboRIO. You have a motor controller and a motor. So this is a sim. This is a Talon. And so what Talon does is, well, most of you guys probably know, but it takes power from the PDP, the power distribution panel, and a PWM signal from the RoboRIO, and from that determines if the magnitude and direction of the rotations on the motor. Also, we have an encoder here. We use these on our drive base and some arms or other mechanisms we would use, especially for autonomous programs. We need to know how far we've moved, and so that we can move to the right spot. And so we'll use those on the drive base. And then this is a bump switch, and it's an example of just a normal digital sensor. Like this one's a little more complicated, but this one's a really simple digital sensor that plugs into the digital input-output ports, and we use that occasionally. Like on that robot, we used it to detect when we had a ball picked up correctly. All right, so this is a picture of the RoboRIO close-up. So first we have a PWM, and we have 10 of those, numbered 0 through 9. And those are for your motor controllers. We have analog in for analog sensors. We also have relays over here, but relays aren't used as much because the Numax control module actually can take care of some relays. Then we have digital I/O. These are for digital sensors and peripherals. We have I2C and RS-232 for serial communication, which previously wasn't available. We have CAN. I'll talk about this even more later, but this is one of the methods that, or this is the method that the PDP and PCM communicate with each other, as well as the RoboRIO. And then we have USB. We have USB host and USB device, Ethernet, and SPI. And that's the expansion port right there in the middle. That actually allows you to get analog out, which is not offered on any of these ports on the edge. So this is the power distribution panel. As you can see, it's got 40 amp channels and 30 amp channels, as well as it powers the VRM.
Yeah, that would melt most of our robots.
Yeah, this is powered by a 12-volt motorcycle battery. So you've got the, yeah, you go grab the battery.
Just to give you an idea of perspective, it takes a lot of power to power this guy.
Wow.
And that thing is drained after 2 minutes.
Yeah.
15 amp hour.
Wow.
So the battery actually has an Anderson connector that plugs into some leads that plug into this housing. These are CAN status lights. The CAN cables that connect all the modules together plug in there. And then these power terminals over here power the other components. Yeah, those are specs. And CAN data that you can get from the PDP is temperature, voltage, and current, to name a few. And so this is the PCM. This is the pneumatics control module. So you would plug in all of your solenoids, which operate the, cylinders or any other pneumatics pistons, and it has.
Say more about that. I don't think most of these robots have a lot of pistons.
Yeah, so actually in FRC, we use a lot of pistons. In fact, last year I think we used the most pistons we've ever used before.
We had like 17 pistons on that robot. I lost count a couple times, but
So the robot, because it uses so much air, it has a compressor on board too.
Oh, yeah.
So it has to, refill its air tanks,
Right.
and it actually has a lot of air tanks. It has 6.
actually there's now 7 because
7.
you're running out.
Okay, 7.
Are those also known as like solenoids, or they work like solenoids?
Yeah, so you have the solenoid. Basically, yeah.
Basically, the solenoid actuates the valve.
Push
Yeah.
air on one side or the other.
What's the PSI on the,
Piston.
It's like 20.
can the,
It's like
It's regulated.
yeah, it's pretty low compared to like what it would take to charge a car tire or something like
yeah,
that.
50, 60 PSI or something?
60 on the,
60 work.
Yeah.
on the outside. 120 internal, and then regulated down to 60.
All right, and so it has 7 solenoid channels. Actually, it has 8. That's incorrect. It has 8 solenoid channels because there's 0. And then the can controls the compressor and the solenoids, and of course the pressure switch. So this is the pressure switch. This is a solenoid, and this is a compressor. Although you can use different parts. They have to be similar though.
How big is that compressor?
It's on this robot. The compressor was not attached, so we didn't bring it.
Is it like the size of that motor?
It's actually bigger than this motor.
Okay.
So it goes right up here where it can
Right.
get a lot of ventilation and cool down easily. So we don't stick it next to all the electronics. And it's going to be about this tall and maybe that long. So it's,
It only weighs around 3 or 4 pounds, Cam.
but it's definitely powerful enough to sustain us through a match.
Yeah. So this is the voltage regulator module. It's not much to talk about this one. Basically, it just provides different voltages and currents. You would use the radio. Like the radio connects to one of these, and I'll talk more about the radio later. And so here you can see the overview again. Now that I've talked about all the parts, it should make a little more sense. One part I didn't talk about though is the main breaker. That's like the power switch for the robot, basically, and like webcam and some more specific parts that not all teams use. All right, so this is a network diagram. So this is where I get to introduce the bridge. So at competition, you have a FMS. So this is the field management system. It controls all of the robots on the field, make sure everything's moving when it's supposed to, and doing what when it's supposed to do it. And so that connects to a wireless router, which connects to a switch, and then those go to your driver stations. And those are boards where you have a laptop and some peripherals. Torrance is going to go get one. Has like joysticks and a button board, or some people use steering wheels to move the robot, but that controls the robot in its teleoperated period. So that's ours from last year.
So the laptop is what's actually sending the commands through the switch to the to the router, which goes back then to the robot. And then we have a button panel over here, so you have one student that can operate all these different buttons, which do tons of different features on the robot. It'll lower this thing, actuate this back, spin up the wheel to shoot. So this is called the operator, the student that stands and uses all these buttons. And the operator is communicating with the driver, which just has simply 2 joysticks. This is a lot like, these joysticks are configured to drive a lot like in a first-person shooter. So this one moves you forward and back, and it can also turn you, and this one can turn you left and right. And so in combination, it makes it really easy for the driver to smoothly drive around the field, and they don't have to do a lot of like stop, turn, stop, turn. And so with enough practice, you can get some really good drivers, and that's a big part of your success in the game, is how good your drivers are for the match.
And so on the other side of the router goes to the bridge, and then your software, which interacts with your hardware, obviously.
Is that a question over there?
Yeah, here.
Yeah.
How long these robots are autonomous?
Oh, the autonomous? Like,
This year, it's only 10 seconds actually. Or, no, sorry, this year it's 15 seconds. Last year it was only 10 seconds. So, for the majority of the autonomous modes, the majority of teams do something very simple, such as drive forward and actuate one part of their robot. One of the reasons why the robot that I showed in the video earlier was able to win the World Championships was because it had such a complicated but successful and consistent autonomous mode that was able to score those 3 yoga balls.
Was anyone else able to score 3 balls?
There's only one other team in the world that can score 3 yoga balls. No other team in the world could score them like we did. We actually built our robot around that concept of scoring 3 yoga balls. Exactly what happens is you only have 10 seconds, and you score bonus points if you're shooting into one of 2 goals that are lit up. And so let's say the goal on the left is lit up at the beginning of the autonomous mode. 5 seconds in, it'll switch to the right side. And so we actually use a camera which is pointing at a human who can provide feedback through hand signals to the robot to tell it to go to the left side or to the right side, depending on which random selection is hot. We call that software Cheesy Vision. It's pretty cool. It actually won us an award. It was awesome.
And the whole
Why
point of
wouldn't
that.
you just, the goal was hot, goal was lit. Why couldn't you just do vision to detect if the goal
We
was
did
lit?
actually. Originally we tried using a infrared sensor on the robot, but the problem was that to detect that we had to precisely aim the sensor at these little reflective panels in the corners of the field, and then someone would unexpectedly bump our robot, and then the whole autonomous mode is messed up. So it was much more consistent for us to just have a human, and as long as the human wasn't sleepy, then the robot would function. So we had a lot of caffeine.
That didn't violate the autonomy rule or the human in the loop?
It's technically illegal now in this year's game. So there was a major change. Major rule changes in the game manual. They specifically added a line that was against using hybrid autonomous modes it definitely was not 100% autonomous, but it was definitely legal, so we used it, and it was really good.
Sounds like cheesecake to me.
Cheesy, yeah.
Cheesy. Yeah, it was kind of cheesy.
the cheese.
Cheesy vision. Yep. Okay, go ahead, Ryan.
All right.
Oh, yeah, wait, one more question.
A brief question. Obviously, you guys have a consistent design aesthetic. To what degree does that play into your success as far as the judging of the contest is concerned? Or is that something that tends to be more of a motivator for the team to have an awesome looking robot?
That's definitely a really good question. There are multiple awards that you could win while at a tournament. The primary award, of course, is the tournament champion, which means you won all the matches, or most of the matches, until you won the whole championship and you beat all the other alliances. But there are other awards. Some of them are technical and some of them are non-technical. Having a good robot aesthetic helps you win those technical awards. Those include awards like the Quality Award, the Industrial Design Award. All of those are judged by, volunteer adult judges that come to the competition and look at your robot. And while it won't guarantee you a win, it definitely helps you have a simpler, cleaner, elegant solution, which the judges definitely prefer over something that is harder for them to understand if it's all complicated and mixed up. So, while the robot is definitely not simple by itself, you can make it look simple, which helps you in the end.
Thank you.
All right. So, while competition network diagram's nice, when you're testing, you don't have all this hardware. So, it looks more like this. You have a wireless router, and your driver station just communicates with your robot that way. Or, in this case, like we will have today when we're demoing our last year's robot, we'll just use an Ethernet link. All right. So now for programming. So you can program the robot now with Java 8, LabVIEW, or C++ on a Linux sock ring system on this robot. It has WPILib for hardware access. That's a library written specifically for this hardware. And it's deployed with SCP over a network. For computers that don't have Ethernet, and if you don't have a wireless connection, there's also a USB device port which functions as an Ethernet adapter, which is pretty neat. You can also SSH into this control system, and that's pretty cool because theoretically you could use something that's not one of these languages as long as you can interact with the hardware. So it's more open-ended, I guess. So this is our programming workflow. So because we have a large team of over 100 members, naturally a lot of them want to program, and so we have to collaborate. So we use GitHub.
You
a lot.
currently have 100 people in your high school team?
We have 109. Our school has 1,600 students.
Mhm.
The vast majority of them participate in athletics, and then all of the nerdy guys do either robotics or speech and debate. Robotics is way cooler than speech and debate. But
Is it more than just the first robotics challenge? Is it the tech challenge and the Lego League and that sort of stuff too? Or
yes,
just your group?
Specifically, our entire team of 109 competes in both the first robotics competition, where we work as one giant team, and we also participate in the VEX robotics competition, which is with
Is that
much
the tech
smaller
challenge?
robots.
Is that the challenge?
It's similar to the first tech challenge, but it's with more store-bought parts. So if you're familiar with the Rector sets, it looks a lot like that.
Thanks.
With bent sheet metal, and so those robots are a lot less interesting to demo, but they're also still cool, and we've done pretty good in that competition too.
All right, so we have a GitHub Enterprise account where we link up all of the people on the team, and we collaborate that way. Java, so we use Java. Our team prefers Java, and so we use Eclipse. First has written some tools that make deployment easy in Eclipse, so it makes more sense to do it that way rather than trying to write our own tools for deployment with another IDE. And we also, this year, we've written something that operates as a test harness that allows robot code to be run on a local computer, so you don't have to test your code on a robot. And so what that does is you have your robot code, you have a simulated robot where you kind of define the way the robot would work. So let's say you're providing power to a motor. You can say if this much power if this motor rotates this many times, then this encoder would rotate this many times. So this is how you could kind of software model a robot. And so this is how you could test functions that aren't like super specific to the robot, the hardware itself, without actually ever touching it, which makes it really nice because not everyone can have their hands on the robot at once. So it's better if we can have people working offline, per se. So.
Specifically relating to the fact that the build season is only 6 weeks long, that means that you don't really even have a robot until about week 5, and so you have only 3 weeks to actually use your robot and make sure that it doesn't like die. So it's definitely useful to have tools like this where you can get a lot of the kinks worked out for the easy stuff, and then you can just use those remaining last weeks with the robot to actually work out the hard stuff.
How many coders that are actually really doing a good contribution to the overall system are operating, all contributing to that GitHub within that 6-week period?
So for students, we have probably 4 really dedicated people.
Okay, so you got a team.
We have like a
Total, yeah, we definitely have a clear distinction between veteran guys that are pushing stuff to the GitHub all the time, and other guys that are more learning as they go.
Because you can lose days if someone messes up.
Correct.
Yeah, and that's also why we use GitHub, because we can roll back if someone makes a big mistake.
What kind of simulation environment are you using?
So it's actually it's interesting. It's all written in Java. So we have a simulated Java robot. We have the library that communicates with the hardware. We've modified such that any calls to the hardware, instead of going to the hardware, they go to a data bank where it saves it, like the state of the hardware. So the simulated robot could access that, and also could set values like sensors. And then the real robot code looks at the library, and to the robot code, it looks the exact same way as it would a real robot. So that's how we plan on doing more offline work.
Does it actually have a graphical component
So
to it? now?
actually, interesting that you ask. We've been writing this data logger system for the robot. So when we are testing it in reality, it serves up a web server with a WebSocket connection to a web browser, and it has a JavaScript thing that plots all the data that's coming off the robot. So that would be really useful for PID tuning and other things like that. All right.
So that concludes our main PowerPoint. What we want to do now is a kind of a combination of Q&A and demo. So the demo I would like to set up first because it will probably give you lots of questions. So take that. Let's get rid of this guy. Actually, no. Let's just slide that table out of the way. And
Where do you want to move?
yeah, let's move the robot. One of the cool tidbits.
Move this table. Oh yeah.
Yeah. One cool tidbit of info is that we name all of our robots after Decepticons, because Decepticons are super cool. So we have Barrage is our most recent robot.
What are Decepticons?
What's a Decepticon? They're the evil version of Autobots, which are both Decepticons and Autobots are Transformers. So
Robots in disguise.
yes, Autobots are cool. Decepticons are even cooler.
How did you guys end up with the number 254?
That number was just randomly assigned to us back in 1999.
Is there a Team Zero?
There, I think, is a Team 1, which actually still exists. I don't think they started at Team 0.
8 is Palo Alto
Yeah.
is Team 8.
Palo Alto.
1 is 192. The 250s were all 99 teams. Former 99.
Okay, so let's hook this up.
They're up to 8,000.
Here, I'm gonna turn off the microphone. Put it down for us.
Okay. Can you turn on the robot? Yeah, that's a good first step.
Now, we don't have liability insurance, so it's not gonna like start throwing the ball at us.
But he's promised he's not going to move.
You actually have to turn it that way so we don't shoot it anyway.
Try not to break it.
Yes. Okay, awesome. Let me back up a little bit.
Aim at the thin glass windows.
So, one of the things that our robot can do is
Defense.
okay.
Aim it at the
Is that
Google
the space?
employees, so there's no liability.
Yeah. So let me just. Oh, are we not connected? Oh, I forgot to enable command. Okay. So
Try Control C.
Control C, exactly. Hey Jared.
Yeah.
It says enabled, but and I'm gonna tell you.
Is the joystick order set correctly?
Maybe. Let's double check.
As they say, demos never go as intended.
Yes, it's the one universal truth in robotics.
That in your thing is just like in yours.
Okay. So let's just do a front exhaust. So that was one button that operated two different systems simultaneously. On the interior of the robot, we have a hinged series of two bars that can independently actuate up. Let me actually, Ryan, you hold this. All right, just don't press any buttons. So you can kind of actually see it in this photo. There's two bars that are individually actuated up by pneumatic pistons, so they can go up like this. And when we shoot the ball, what's actually going to happen is both will come up at the same time and clap together. Because of that clapping, we actually call it a pinniped, which is the scientific name for a seal, because it claps like that. Yeah, exactly. But because they're individually actuated, we're able to just use one and push the ball out the front of the robot and push the ball out the back. That's a really important feature for any of the robots to have last year, because you had to pass the ball from one robot to the other to score extra points. And so this allows us to have the ball in our robot, and instead of just scoring it, we can just set it on the ground for another robot to take it. So it's a really controlled maneuver with the ball that is preferable. So now, Ryan, you're going to press.
Do you want to do the front intake or?
Yeah, so first we'll show how we can pick up a ball. So that intake roller has a black roller, the horizontal roller you can see on the photo in the front there. The black roller spins and sucks in the ball as the angled weldment comes down over the ball. So we'll get rid of it,
Sample return.
and then we'll Go ahead, just roll it in one more time. And one of the features that we tried to design around was making it so it can pick up the ball kind of from the side. You don't have to be straight on, which helps a lot with driver ease and ability. So we're now going to go to shooter speed 1. Our shooter system is actually the part of the robot I worked on the most. It was super cool. I like to brag about it a lot. The front in the roller there, you can see. So this and this is a large black rubber flywheel that's very, very heavy and has a large moment of inertia. So when we spin this up, we actually use 2 pretty large beefy motors to spin that up. You can see this is one of the motors we use to spin that. And this motor will get up to, our max speed is 5,000 RPM. We're not going to 5,000 RPM indoors, but it's very loud. We will use that when we're shooting the ball in a Hail Mary across the field. But most of the time, we're spinning at a much slower speed. It's much more controlled, and we fine-tune the robot around those slower speeds. The way we're able to get multiple speeds, actually, is we have a retroreflective sensor that's looking at the side of this wheel. And every time a piece of silver tape passes that retroreflective sensor, it counts a revolution. So rather than putting some kind of encoder on it, we actually can put a sensor which kind of replicates a potentiometer. So Ryan mentioned we used encoders on the drive to count revolutions. We're doing the same thing here, but with a different type of sensor, so it's kind of fun. So this flywheel spins up really fast, the pinniped claps together, and the ball then gets squeezed in between this curved hood and the shooter flywheel. So it actually, because of the friction against the back of this, it provides a backspin on the ball, which also helps increase accuracy rather than just like punching the ball where it would wobble around. Like that's simple physics with like golf balls. Why golf balls have dimples and stuff too. The spin helps increase accuracy. So
How did you deal with the various pressures that the balls were inflated?
You pray mostly, and you hope that they're all to the regulated pressure. You also provide extra compression on the ball, so it kind of eliminates some of those variables. It's pretty difficult for me to actually get this ball out of here because of the compression on it. But that kind of helps you, make it a little bit more accurate. The final cool thing is we'll show you, we actually have a 2-position hood. So currently this hood is in the forward position, and these pneumatic cylinders in the back are fired up, which triggers a toggle that pushes this curved piece forward, providing a lower release angle and also a farther shot. So we'll use this when we're farther away from the goal. And then when we get right up close to the goal, you saw in the match, we would sometimes drive right up to that low goal and shoot basically straight up in the air, only about 2 feet forward. We'll actually pull the hood back like this, and that shortens the length of the hood, increasing the release angle, giving you 2 different positions. So that combination of a 2-position hood and a multi-speed flywheel allows us to shoot from like 6 different spots on the field, whichever is the easiest for us to shoot at. And so that definitely helped us be super versatile during a match. We can shoot, you give us the ball, we'll get it in the goal. Don't worry, we don't have to be in any specific spot.
That's not going to do anything for you this year, though, right?
No, not really. So, yeah, enable it. So we'll spin up the flywheel here, and then. Can you take it, Nick? You can actually hear the compressor running. We used quite a bit of pressure to launch both those pinnipeds, so the compressor is now reestablishing our preferred PSI. It uses active control to make sure that we never fall below our desired limit.
What's a pinniped? Are you referring to this ball?
No, the pinniped, I mentioned, the pinniped is that system here in the center that actually claps together and pushes the ball up into the shooter. So the one other cool trick we can do with this is, oh, there goes the compressor. The one other cool trick we can do is we can open up the whole back of this robot, which gets rid of all that compression, and at the same time we spin the flywheel backwards so that you can actually throw the ball in from a human into the robot, and it will actively help to catch the ball. And that's a much faster system than just having like a human, drop it onto the field and then it bounces around and rolls away and then you look stupid. So it's much easier if you just throw it at the robot, but you have to have that back part open for it to actually catch. So whoever's feeling strong, you got to throw a lot of force. If you haven't seen it yet, we've got a great little target right here. This is aim here.
Target is not a sponsor, although.
Target is not a sponsor, but
That is a trademark infringement.
It's educational purposes.
educational, yeah. Okay, so let's do. And this is the No, I'm not gonna shoot. There's the other position on the hood. You can see what this looks like now. With this back, it'll be a high release angle. I don't want to shoot that in here or it'll smash the roof. So, yeah, definitely not part of the contract. Okay, so I guess the one other thing we didn't show is it can drive. It can drive really fast, actually, almost 20 feet per second when it gets up to its top speed. So that field, for perspective, is 60 feet long, so it's almost the length of this whole room. And our robot can cross that field in about 15 seconds or less. Maybe.
It's like three.
Well, if there's no one in the way, 15 with robots, you gotta go around people. Okay, so that concludes the main part of our demo and our talk and stuff, but we'd really love to answer questions if we have time. So, yeah, in the back.
Would you consider making it omnidirectional?
As in omnidirectional with the wheels?
Straight from here or whatever.
That's definitely something that we considered, and it's something that a lot of really good teams do. Actually, I'm gonna go, if I can pull this up, I wanna go back. One of the coolest robots that was in that final match with us actually had, way too far. Wait. So, I'm gonna pause it, I think.
It's the yellow one, right?
The reason I'm showing you this is I want you to see. Oops, no, darn it.
It's the yellow one.
Okay, so this yellow robot, Team 16, it's a yellow robot with a red bumper, but Team 1640 is actually a robot with full swerve capability. So if you look at it drive, it's actually not moving in straight lines relative to the frame. It can fully turn all of its wheels 360 degrees. So you'll see that down here. They're going to try to drive around us, and they're driving sideways right there. Now they're pushing into us laterally. So it's definitely a really good feature to have.
But you can also get pushed around a lot.
But now I gotta talk about the cons, and the reason why all of our robots for the past like 5 years have all been a very straightforward 6-wheel or 8-wheel drive. So you can see 1, 2, 3 wheels on this side, 3 on the other. The straight wheel alignment is extremely simple and lightweight, which makes it so we can focus our efforts in the 6-week build season on other parts of the robot. Teams that build these really complicated, fully turning things, or they use more complicated omni wheels with fancier programming to just allow them to strafe in that method also. All of those teams typically have a heavier drive base. They spend more time making it, more time tuning it, and it breaks down more often. So we prefer to use a tried and true 6-wheel drive, and then just train our drivers to be super good and build the rest of the robot to the best of its ability. Yeah.
In this year's game, how much do you have to rely on your allies?
Let me pull up the image just while I talk about it. So this year's game is definitely an interesting one because there's this clear division between red and blue, and you're not really allowed to interact with the enemy alliance. It means that you have to work a lot more closely with the members on your alliance. Also, you're only working now in half of the field compared to last year. You had the whole length. So you're kind of afraid of bumping into your other alliance robots. So there's definitely some coordination that's required. The major rule of thumb, though, with our team especially, is that we never design our robot to be dependent upon another robot. Because the way that the match scheduling works, the way the matches are played out, you're randomly paired with people and you're randomly paired against other people. So you can't guarantee that you're going to be with that robot that can, for example, in this game, put the recycling cans on top. That's a huge point value. If you don't happen to be with that robot in that match, then you're going to be getting way less points than you could have. So our rule of thumb is always design a robot that can operate independently to the best of its ability and not have to rely on anyone else. And when you do have partners, especially really good partners, then it's just an exponential boom over what you could have gotten originally, rather than being a detriment for when you have so-so or the average partner.
Are you allowed to coordinate a strategy with your other partners during each match?
Definitely. Before the match, you actually have quite a bit of time when you're standing in line and waiting, and you can be talking with your partners. This year, the strategy might be simpler to communicate because all you have to do is just say like, okay, I'm going to be in this corner, you're in that corner, and third robot's over there. And that way you won't bump into each other, boom, boom, strategy's done. But sometimes, if your robot's dependent on others, you will have to strategize with them. Or, if we remember, last year's game with this robot, the amount of strategy that went into a match was ridiculous. You had to pass the ball between different robots, and you had to do it in certain colored zones. So you had to be in the correct spot on the field at the right time to be the correct robot to receive the ball. Then you had to know what to do next, like throw it over the truss or something. So all of those different steps were something that we talked about. One cool thing is last year we actually made play cards, like in football, where you like have a laminated sheet and you draw out the path that everyone's gonna go. We had stuff like that, but for robots. And so we'd be like, oh, you go over there, you go over here, and together it would, with our partners, it allowed us to make really effective strategies for each match. Yeah. So in the majority of the tournament, as in like Friday and Saturday, of a 3-day tournament, Friday, Saturday, Sunday, for the Friday and Saturday days, you're mostly playing only qualification matches where you're randomly partnered with people. And so no one really wins when you win a match. It just places your robot higher relative to the robots that lose. However, when you get to Sunday, you have to do playoffs where you pick the number 1 robot will pick some other robot, usually the number 2 robot, and then the number 3 robot can pick usually the number 4 robot, but it can vary depending on if you want to play a specific strategy. So it's at that point when you get to the elimination matches where the teams that you pick, if you win, those will be the teams that also receive the exact same trophy, the same medal, the same blue banner.
Were you guys the pickers or the pickees?
It varies.
But for the championship,
for the championship, we were the number 1 seed.
Okay, so you guys got to pick.
Yeah. So in our division of 100 teams, we played 10 matches. We didn't lose a single one. And so that placed us at the number 1 spot. And we picked the number 4 robot because they were super good. And that was team 469. And then the other alliances actually got to pick. So it went like the first pick, then the second. So 1, 2, 3, 4, 5, 6, 7, 8. And once you get to 8, it actually goes back serpentine. So it goes 8, 7, 6, 5, 4, 3, 2, 1. So our number 1 pick was the best robot in our opinion, but our second pick for our third robot was pretty low on our totem pole, but pretty high relative to the other 50 teams. So there's definitely a ton of strategy that is not, you don't even have to know how the robot works to help with that kind of strategy, where you're choosing which team to pick, who are we going to play with, how is that going to be better than this robot, stuff like that. Yeah?
Do you have a strategy for this year's robot, or are you still very much in the brainstorming phase?
We definitely have a strategy. I'm not really allowed to share it with you because it may vary, and we also want to kind of keep it secret until our robot's revealed. Once you see our robot, you will instantly know what our strategy is. I'll just put it that way. But definitely the strategy portion of the game is one of my favorites because it's where your team has the most flexibility. And last year, our big strategy decision was to do that 3-ball autonomous mode, and that ended up being really good for us. We designed our whole robot around that, and it was awesome. So we just gotta hope.
Are you going to do a 3-object autonomous mode this time?
Very likely.
Okay.
I'll say that. Yeah.
Has that robot ever lost?
Has this robot ever lost? Yes, it has. In addition to losing matches. Just, occasionally we get randomly paired against 2 or 3 really, really good robots that are just as good as us, and there's no way that we can beat them. We just lose that one match. We got lucky at the World Championships and didn't have that happen, so we were able to get undefeated for those qualifications. But this robot's been in many competitions. In the reveal video, you saw that we mentioned the Central Valley Regional, which is in the city of Madera, the Silicon Valley Regional, which is in San Jose. That's actually coming up if you guys want to check that out. That's in San Jose at San Jose State.
I think it's the same time as Robo Games.
Oh, really? That's terrible timing. Okay. Well, if you don't want to go to Robo Games, or you're unable to, I'll just say that FRC events are free admission. Okay. Okay. Robo Games is awesome. I'm not dissing Robo Games at all. That's okay. That's my big selling point.
You'll do well, Andrew. You'll do well.
And then the third regional we went to last year with this robot was actually Waterloo, Canada. So we flew to New York and then drove into Canada and competed against the second best robot in the world. If we were the number 1, it was the team that we were fighting in the finals of Einstein. It was Team 1114, Symbotics. We're the big blue robot. They're the big red robot. So it was really awesome. We ended up beating them and winning Waterloo. So in the end, this robot won 3 regionals. Then it won its division at the World Championships. Then it won the World Championships. Then we took it to off-season events, which are not run by FIRST, but rather by teams, and are just more loose on the rules and a bit more fun and open-ended, but they still give trophies and awards. And so we took this robot to 3 off-seasons. The first was IRI, Indiana Robotics Invitational. We got invited to this prestigious elite tournament in Indiana. I don't know why, it was the most prestigious is in Indiana, but it was an awesome tournament. We competed against the best teams in the world. Andy Mark's in Indiana, sure. But we ended up, that was the one tournament we did not win. So we became finalists at IRI, 2nd place. It's kind of bummer, but if we win every tournament, that would be no fun for the other teams. So you gotta lose one.
So it is possible for you to lose.
Yes, we have lost.
You've lost one time.
We've lost one. Yeah, we lost one off season. Then the next 2 off seasons we went to, the second one was Cheesy Champs. It's at Cheesy Champs. That sounds familiar. We're Cheesy Poofs. Yeah, Cheesy Champs was an off season that we ran at our school. We had 38 teams there. It was super cool. We weren't aiming to win our own tournament, but we got picked, and so we won.
Did you go to WRRF?
WRRF did not help run our tournament, but there's another tournament they run called Cal Games.
Yeah, you guys were there, weren't you?
We did not go this year because we were busy planning for Cheesy Champs, but Cal Games is a tournament we've gone to in the past, and we've done pretty well there sometimes.
Yeah.
And then the third off season we went to was Madtown Throwdown, also in Madera, and we ended up winning that too. So this robot has definitely been successful. It also has a lot of battle scars. If you look at this later, you'll see it's not as pretty as it is in the picture I was showing you. There's scratches and dents, and this bumper's all ripped up, and my gosh.
Yeah. It's all right.
How much more time do we have?
Probably about 2 more questions.
2 more questions. Okay, yeah.
For operating effectively as a team, how does that work? You have a crew chief. I see you've got 2 people actually controlling the robot. You've got people interacting from the sidelines, throwing balls in and so forth. How does that work? Who's the boss? How do you coordinate?
So we have a drive team which consists of 4 people. 3 of them have to be students, and those 3 are the driver, the operator, and the human player. The human player is the person who last year threw the ball into the robot. This year, the human player actually stands right here and can put these gray totes into the field for more totes onto the field. So the human player helps a little bit. And then the 4th member of that team can either be a student or an adult mentor. And that person's called the drive coach, and they're the ultimate strategist when it comes to what your drive team is going to be doing. So typically the driver and the operator are simply controlling the robot. They're watching the robot, but that adult or student coach is the person who stands behind them, and they're watching the entire field. They're watching the clock. How many more seconds do we have? They're talking to the other coaches. Where are you going? Where are you going? Okay, you go next. So it's a combination of the coach telling the drivers and the operator what to do, and that chain of command helps make drive teams really efficient. Okay, one more question.
How much does it cost?
So technically, the limit of the robot on all of the components it can have, excluding electrical components and pneumatics systems, is $4,000. So that includes extra electronics like sensors and stuff, but it excludes stuff like the main electronics, like the RoboRIO and stuff we were showing earlier. The way that we are able to build fancy robots for relatively low amounts of money is by having a lot of sponsors. So this side panel, you can see if you lean forward or we get a camera. Oh yeah, it's on the camera. So, oh, it's on the back of Ryan's shirt too. Yeah, we have like NASCAR shirts. It's super cool. But we put all of our sponsors on the side of our robots to give them recognition, and those sponsors either give us money or they give us like in-kind donations such as welding, powder coating, anodizing, water jet, all these different tools we use to build the robot. That's all for it. Okay.
Thank you very, very much. Very exciting talk. I'm sure you can ask lots of questions afterwards. Thank you for not driving it around and for not killing anybody. Okay.